Okay, so this talk is only tenuously connected with the topic of domain-driven design, but I am going to show you a lot of models, very different kind of models from what we normally talk about in domain-driven design, and they are all going to be in a domain with which you are very familiar, which is the domain of software development itself. So let's go. So I guess you're all familiar, I hope you're all familiar with the basic form of the scientific method. So we ask a question, we have some question we like to answer about the way the universe works, we can formulate a hypothesis about how we think it works, we can go ahead and perform some experiments, ideally controlled experiments, to determine how the world actually works, collect data from those, and draw some conclusions. And then, normally, we then either accept the hypothesis as being a realistic description of how the universe works, or we reject it and come up with a better one. Now, I would love to be able to do controlled experiments on what we are all involved in, which is the process of software development itself. Unfortunately, this is extremely troublesome for many reasons. Developers don't like to be watched. Many of us are introverts, including the ones who stand up on stages in front of lots of people. It's difficult to eliminate or control for lots of different confounding factors when you're designing an experiment. When people have designed experiments and tried to do experimental studies on the process of software engineering, often that's done with toy problems, which aren't representative of the kind of problems we deal with in larger systems every day. No two projects are the same anyway. We certainly can't do double-blind experiments. It's very difficult to have people develop software without them knowing what they're developing. The whole point of DDD is that we know what we're developing and why. And often experiments are done in a university setting with students who have little or no real-world experience. And above all, doing experiments costs time and money. And this is only a trillion-dollar industry. So, what can we do? Well, it turns out there are other fields of scientific endeavor where performing experiments is hard. If you want to know how galactic collisions work, or how plate tectonics work, those things are equally difficult to perform experiments with, right? There are problems with this. It's very expensive to collide galaxies. We don't have anywhere big enough to do it. So, there's a different flavor of the scientific method, which we use. And it looks something like this. Again, we start with a prediction, a hypothesis, about how we think the universe works. But then we go ahead and we do some modeling. We construct a model, a simulation, if you like, often these days within a computer with software, to simulate how we think the universe works. We then make some observations from both reality and from our simulations and compare those observations and go around this loop many times, comparing and tuning our models until what our models produce agrees with what we see in the real world. And at that point, we can then look at how our models are constructed and hopefully extract some useful knowledge from those models. So this is a different flavor of the scientific method. And my background way back was in the earth sciences, and this is very much how the earth sciences proceed, because we just don't have millions of years of lab time to do experiments. So I'm going to show you a couple of models today. I am going to show you a model in the first section, which I have constructed. The second one is also a model I've constructed, but it's based very much on what's been published in the literature in a field I'm going to talk about called software process dynamics. And then very briefly at the end, I am going to give you some pointers for how to create your own models. We're not going to have much time for that today, so if you are interested in taking this further, do come and find me afterwards. So we have quite a few people here. I can only really see the people in the lower area. But I'd like anybody who has moved from working on one software system to another software system any time in the last 64 years to stand up. That should be all of you. Right, so everyone's standing up. So if that's still true for 32 years, remain standing. Otherwise, sit down. Is it still true for 16 years? 8 years? 4 years? 2 years. Okay, so we're getting on for half of people sitting down now, and then 2 years was the last one I did, and then 1 year. Okay, so what we've just done is measure the half-life. You can all sit down now. Actually, no, you can stand up the whole time. What we've just done is measure the half-life of developers with respect to software projects, right? How often does it take for half of the people on projects in aggregate to move on to other projects? And I've done some research on this, and I very often do this exercise that we've just done. And it turns out the answer is about 3.1 years. Every 3.1 years on average, you can expect to lose half of the people you work with now because they're going to go somewhere else. Okay, there's turnover. And I like half-life as a concept because we can measure the half-life of plenty of other things. And I don't have time to go through all of these today, but things like the lifetime of enterprise applications, the half-life of enterprise applications, the half-life of chief executives. How long does it take to replace half of chief executives? Lines of code. Look on my slide here. See how these numbers are getting bigger? It takes 13 years on systems I've looked at, and that's a lot of systems, including open source code, for half of the lines of code to be replaced. That's because we mostly add code and very rarely delete it. And the larger the software entities we deal with, typically, classes, 37 years. I've worked on systems where the module half-life was 58 years. That doesn't mean the system existed for that long. Of course, you can do the math and figure out how long these half-life figures are. So the key point here is that developers are transient things compared to the systems they work on, right? We're moving through systems much more rapidly than the code actually moves through the systems we work on. So this would be an interesting number to plug into any kind of simulation we wanted to make of the process of software development. Another number we need is how productive people are. I'm going to flag a health warning here. I'm going to use lines of code, right? Sharp intake of breath from the audience there. That's, you can come up with a better measure. The thing about lines of code is it's universal, right? And I'm not claiming that a metric ton of aluminium has the same properties as a metric ton of steel, or that a million lines of F# has the same qualities as a million lines of Python, right? But it is a standardized measure that we can begin to ask questions about, and it is something where some data has been published. So let's look at developers. And we have a minimum modal and maximum productivity here in lines of code per year. And this is, I think, where the fabled 10x developer fact or myth arises from. So you can see my minimally productive developer is cranking out about 2,000 lines of code. The maximally productive developer is about 30,000 lines of code a year. But the mode is very much towards the low end. So I only have 3 numbers, so I'm going to do what any modeler does and put a triangular distribution through that. We can create a cumulative distribution function from that, so cumulative probability across there on the vertical axis. And this enables us to sample in a computer model development teams. Okay, so if I wanted to create a team of 10 developers, this is the process you go through a cumulative distribution function. And you can see that the yellow dots along the bottom there, most of the developers are at the low end of the scale where we would expect them to be, and we have a few up at the top end. That's maybe a little bit difficult to digest in a few minutes. Another way of looking at this is that a typical development team looks like this, right? In terms of the contribution, in terms of code people make to projects. If you've worked on a project with 7 or 9 or 10 people, 2 or 3 people are usually responsible for most of the contribution in terms of code. That doesn't sound too unrealistic, does it? Turns out, though, that people's productivity is controlled by many other factors, not least the size of the system they're working on. I can write a 20-line script starting with 0 lines really quickly, but adding 20 lines of code to a 1,000,000-line system might take me 2 weeks, right? So it's highly nonlinear with respect to the size of the system to which we're adding. So that effect can be measured as well, and I'm giving figures here that I've collected or researched from the literature. Of course, you would like to calibrate these on your own systems, and it's quite easy and possible to do that. So you see that developers become dramatically less productive on larger systems. I'll point out the logarithmic scale on both axes here. So the most productive developers go from 30,000 lines of code a year down to 5,000 as you go up to 100 million line computer systems. So we've got some numbers. Let's do some simulation. So here's a 5-year timeline. Let's simulate a typical Scrum team of 7 people over 5 years and see what they can produce. So what you're seeing here is a kind of stream diagram where the vertical thickness of this wedge is how much code we have accumulated at that point in time. So we start with no code, and code accumulates over time. And each colored stream is the contribution of a different developer. So this is just a single randomly generated realization. So we start with nothing at day 0. Some developers, like the blue developer here, contribute more. You can see that their wedge is growing relatively quickly. Some, like the brown stream here, that person is contributing less. When a developer leaves in this model, because remember I have turnover built in here, when a developer leaves, I just, for the purposes of keeping things simple, I just freeze their contribution forever. That sounds like a very naive modeling assumption. It turns out to be quite true. People's code just gets fossilized in the system. So when a developer leaves, their contribution's frozen, fossilized, and I immediately replace them. We have a very efficient hiring and human resources department in my simulation, and they are immediately replaced by a new developer drawn from the same distribution. Because of tendency towards the mean, really good developers tend to be replaced by less productive developers, and really low productivity developers tend to be replaced by more productive developers. So there is a tendency to the mean here, and you cannot escape that. So my scenario here says after 5 years, we have 235,000 lines of code written by a total of 19 people. What happened to my team of 7? I wanted a team of 7, I got a team of 19. Okay? Systems written by 19 people look very different from systems written by 7 people. And at the end, only 37% of the code is written by people in the current team. That's an important number. All that code that you can't talk to anybody about, there it is. So this is completely fictitious. And that's a single run of a simulation. Of course, once we have a simulator, we can run it a lot. We can do Monte Carlo simulation, and then we can begin to do statistics on the distributions that pop out of hundreds or thousands of simulations. So we can begin to do things like putting confidence limits on the numbers. So for a 3-year project with 7 people, we would expect 11 people through that project as the mean, plus or minus 2 at 1 standard deviation. Right? So when you're thinking about your Scrum team of 7, it's really a Scrum team of 11. Okay? And we can make a prediction about how much code we would expect them to have at the end of those 3 years. And we can say that 70% of that code at the end is written by people who are still there. It's important to calibrate these things against reality. This is a visualization of a project, of a simulation of a project I worked on for 8 years. And I used this simulation to calibrate against the actual data I had from that system, which unfortunately I'm not able to show you today. And so it's a 20-year project, and in reality we produced 2.1 million lines of code, C++, lucky us. And the simulation says we expected to produce about 1.8 million. Those numbers aren't vastly different. I think there's something in this technique. What's interesting is our team of 21 was really a team of 114, and in reality it was over 120. Okay, so a lot of people have been through the system. That's why there are 114 stripes here. And you can see that even the best developers, in terms of productivity measured in terms of lines of code, maybe that's the worst developers, have a relatively small impact on the overall system, in terms of the mass of the system, at least. Of course, when you have these kind of simulations, you can begin to ask other interesting questions. Well, how long does it take for 7 people to produce 100,000 lines of code over lots of simulations? And the distribution looks like this. This shows the probability of delivery on any particular day. So it's never less than 200 days, and it's rarely more than 700 days, or never more than 700 days here. Again, it's easier to look at these it's more useful, although maybe less intuitive, to look at these on a cumulative distribution, which allows us to ask questions or frame the question this way. So we can say, well, in 80% of simulations, they finish before day 470, and in only 20% of simulations, they finish before day 330. So that's quite a narrow range in terms of days, I think. I think that's quite interesting. And then we can look at what I call the proportion of code that is written by the current team. So if you want a take-home figure from this part of the presentation, you can take this away. After 20 years, 20% of your code will be written by the current team. And that turns out to be invariant on the size of the team and all kinds of other factors. That's a good take-home number if you want one. So let's move on. Yes. I took this picture this morning. This is bang up to date. So I would just like to, obviously, I'm not going to reiterate Conway's law now, especially in front of the great man himself. But I would like to add a qualifier, I think, which is that the structure and the qualities of systems are a function not just of the shape and organization of the team, but you have to integrate that with respect to time. Teams are not static. You work on a 20-year-old system, and you think how many times those teams will have been reorganized over 20 years, right? I've worked in organizations where you get reorganized, every few months, it seems. So integrated over time. Okay, so that was Conway's law. Let's move on and quickly look at another law. You probably know where I'm going here. So this is the Mythical Man Month, Fred Brooks' classic book. And of course, the joke is that you should buy your manager 3 copies of this book so they can read it 3 times more quickly. Does anybody know what the picture on the cover of Fred Brooks' book is? It's the La Brea tar pits, which is currently kind of in suburban Los Angeles. Well worth a visit. And of course, one of the chapters in the book is called Out of the Tar Pit. But the reason we have Fred Brooks' book here is to remind us of Brooks' law, which is adding manpower to a late software project makes it later. And it's presented to us as a law. And laws are things which are always true. They are invariants about the way the universe works. So let's ask ourselves critically whether this is true and try to test the hypothesis that it is true. How can we do that? Well, I've given you the conceptual tool you need, which is the scientific method, and the variation of it that says, well, okay, let's make a simulation of Brooks' law, right, in the computer, and then we can play with it and discover if it's always true, or if we can discover circumstances where it appears not to be true. So let's do that. So the previous model I showed you of the accumulating code was what's called a discrete simulation. So it dealt with individuals. I was simulating individual developers, populations of those developers. There were definite events, people being hired, people leaving, people writing code every day. I dealt with probability distributions to characterize the populations. It was a stochastic model, so I need to run it multiple times in a Monte Carlo simulation in order to collect statistics about the aggregate behavior, and each simulation is a concrete scenario. And they can be quite tricky to formulate as code. Not very tricky, but there are some issues there. I'm going to show you a different type of software simulation now, a continuous simulation. These deal with aggregates, not aggregates in the domain-driven design sense, but aggregates in terms of stocks of things, like a collection of people. These aggregates are analog quantities. We allow ourselves to have 3.2 developers, okay, or 7.5 lines of code. We give ourselves that freedom. We deal with levels of these quantities and flow rates between quantities. These are often called stocks and flows simulations. And now, rather than modeling them with events, we model them with equations, or we can, which we then have to solve either numerically or analytically if we're lucky, but usually numerically. And these are much more abstract way of formulating the problem because you're never dealing with a concrete scenario, you're dealing with a problem in the abstract. But they are easier to formulate as code. So let's look at the essential ingredients of one of these models. So it's a very simple model of not just a software company, but any company really that employs people. Maybe companies that employ people won't be a thing soon. So we have the number of personnel in the company. We have a hiring rate, which is the flow of people into the company as they are hired. And the pool of people outside the company is just assumed to be infinitely large, right? That's essentially outside the model. And we have an attrition rate. We have people resigning or being fired or dying or retiring, or all of these different things are captured in the attrition rate, and they go back into the pool outside the model, okay? And we control the hiring rate usually with a desired personnel level. We know how many people we would like to have in our organization. So this is very simple. So we have sources, which are outside the model boundary. We have sinks, which are also outside the model boundary. We have levels of a repository, some analog quantity inside the model boundary. We have flow rates between these things. And we have what, in these type of models, we call auxiliaries, which are constants or scorekeeping variables, like how many people we would like to have. Okay? Okay, so Brooks' law. We need a reference behavior for Brooks' law. It's very simple. We increase the number of personnel, and the productivity goes down at that point, right? And because the productivity goes down, it takes longer to do whatever it is that we're doing. Okay, so the reference behavior for Brooks' law is very simple. We just need to make a simulator that reproduces this behavior, and then we can play with it and discover some useful things about Brooks' law. So let's make a Brooks' law model using the tools, the conceptual components I've just given you. So what do software companies do, or software organizations do? They are simple engines which convert unrealized requirements into developed software, right? That is what happens. Requirements go in at one end, software comes out at the other. Of course, the art of modeling is what you leave out, right? So of course, this is simple, but it's not so simple that it isn't useful, okay? So this is about the simplest possible model of a software company, and there is a rate at which we convert requirements into code, okay? What controls that rate? Well, that's controlled by the nominal productivity of a developer and how many developers we have, right? Now, I'm not using lines of code in this one. I think I'm using function points, right? Which is something else you probably disagree with even more than lines of code. However, it's another way of measuring requirements in particular, and we can have an unrealized function point and a realized function point. So we have a rate in terms of how many function points per developer per day we can pump through this system based on how many personnel we have. With it so far? It's simple, right? And we can run our simulator and we can say that, okay, we start with 500 function points. It doesn't matter how big a function point is. This is just normalized for my notion of function point. We have 20 personnel. Each person converts 0.1 function points a day into code, okay? Some simple arithmetic later, you can do this one in your head, and you'll realize that it takes 250 days at this constant rate to convert everything into code. So that's too simple, right? It's not a very interesting simulator. So let's make it more interesting. Let's differentiate the idea of personnel into two categories. We have inexperienced personnel, not familiar with this code, and we have experienced personnel, who are, they know their way around, they're more effective on this particular project, they understand the domain, they know how the system's put together. And we'll have an assimilation rate at which inexperienced people become experienced people, okay? And of course, they all feed into the software development rate. So now we still have 500 function points, and we start with 20 inexperienced people, and they're only 80% as productive. And so now, of course, it takes longer, right? It takes 313 days, rather than 250 days. Still very simple, but slightly richer model than we had previously. Okay. Now we want some control on this assimilation rate. So in the previous run of the model, everybody just stayed inexperienced. Now we want them to learn stuff, right? So we're going to simulate them learning stuff by them becoming experienced. So we need to control this assimilation rate, which is the rate from new personnel to experienced personnel, and that needs to be controlled by the number of new personnel we have. Because if we have no new personnel, that rate has to be 0, right? And when you see levels of things and the rate of thing is a function of the level of the thing, you're thinking about differential equations and all these things and exponentials, and you'd be completely right. So that's all happening behind the scenes, but we don't need to worry about that at this level in the talk. So now, we start with our inexperienced personnel, and we set an assimilation delay, which is a way of quantifying how long it takes for someone to become experienced, of 20 days. And now, as the inexperienced people become experienced, you can see the curve rising there. As they become more productive, we can see that the total project time is shortened down to 215 days. Remember, we started with 250. Okay, so our model's getting a little bit more interesting, and it's showing some behaviors. Okay, but all these people learning in this model, that has a cost, right? It takes the time of the people who are already there to explain to the new people how the software is put together, help them understand the domain, okay? So there's a training overhead. It takes time for people to get to grips with the system. And so we would like to model the training cost. Okay? Sound reasonable? Okay. So we're going to have a training overhead here. So now our simulation changes a bit. We still have the 500 function points. We have 20 inexperienced personnel at the beginning. We have a 20-day assimilation delay. And we're going to say that 25% of an experienced person is needed for training each inexperienced person during assimilation. Okay? So a quarter of somebody's time is going to go on helping the new folks on the project. I think this is interesting because look what's happened to the completion time. It's now 220 days. Okay? So the purple line here next to the red line, it's just very slightly longer. So even though we're going to use a quarter of people's time on training at the beginning, the effect on the completion date is minimal. So training is, in this instance, seems to be quite a cheap and effective thing to do. Okay. So now we need to get to the core of what I think Fred Brooks was talking about, or hinting at, which is that as we add people to a project, it takes longer. Why does it take longer? Because there are more people, right? Why does having more people make things take longer? Because they all have to talk to each other, right? And that's not linear, is it? Right? Having 4 people in a project doesn't take 4 times as long. There isn't 4 times as much communication as having 1 person, right? There's a lot more, because obviously 1 person can't communicate with anybody. So, let's build in a factor for communication overhead. So how do we model the communication overhead? Well, obviously the communication overhead depends on how many people we have in the project, irrespective of whether they are new or experienced. So we need to sum those 2 quantities with the yellow and the orange arrow there into that blue thing that says communication overhead, and that feeds into the software development rate as well. This time as a negative thing. It's going to detract from the overall software development rate, because we're going to be sitting around in meetings rather than talking to our clients or writing code. So here we are, simulation E, 500 function points, 20 inexperienced personnel, 20-day simulation day, 25% training overhead, and a published communication overhead model called the Abdel-Hamid quadratic communication overhead, which sounds much more complicated than it is. It's basically just saying its communication overhead is proportional to the square, and these guys did some experiments, the square of the number of people, and these guys just actually did some experiments and measured how that communication overhead is what the constant of proportionality in there is. So that's a published model. And you can see that as we add in communication overhead, we're onto this lower curve here, the kind of grayish, greenish curve, E there, you'll see that the completion time was extended quite significantly out to 286 days to completion. Okay, so the model's getting more interesting now. But we're not quite at the point of dealing with Brooks' law. So one of the questions you might have is, well, you know, where's he getting these numbers from? How does he know it's a 20-day assimilation delay? Well, I don't. But I can turn that around and say, well, how important is it that it's 20 days versus 15 days or 10 days or 100 days or whatever? How do we figure these numbers out? So one of the things we need to do in these kind of simulations is what's called sensitivity analysis, which is to basically play around with the dials on the model and see how much effect they have on the output. And if the answer is not very much effect on the output, then we don't need to invest very much effort in deciding where to set the dial, right? So let's play with the assimilation delay here. So here I have an assimilation delay of 10 days, 20 days, and 30 days. Okay? And you'll see that at the front end of the curve there, it looks like there's going to be a really big difference, doesn't it? Those curves are diverging quite significantly. Whereas if you look at the completion date at the end, they're pretty tightly clustered. And if you look at the days, we're talking about a difference between 280 days at the minimum and 292 days at the maximum. So it's a really tight range. So basically, I'm not going to worry too much about exactly whether that number is 10, 20, 30, or 50, or whatever, right? It's important that the effect is in the model somehow, right? And if we had time, I would go through how you do sensitivity analysis on all the other things, but I just want to convey the idea of doing a sensitivity analysis on the numbers that you plug into the model so you can figure out where to invest your effort in determining which ones are really important in controlling the output. Of course, if you discover that some aspects of the model basically have no effect, what should you do? You should take them out of the model and have a simpler model. Okay. So to really make any model interesting, you need a feedback loop, right? Models which are just forward only tend not to exhibit very exciting behaviors. But as soon as you put feedback loops in, things tend to get much more interesting. So the feedback loop wrapping around the outside here from developed software back into personnel allocation rate, you need to imagine there is a misguided or maybe enlightened manager sitting in that feedback loop saying, oh my God, we haven't developed enough software yet. What are we going to do? We're going to hire more people, right? So that's the Brooks law effect. Okay, so that purple arrow around the outside includes some human input in terms of a management decision. Okay, so just to show you how these things are very, very simple to formulate in code. All these fabulous pictures I'm showing you are not, I'm afraid, the result of some incredible visual programming environment. It's literally like 200 lines of code to put these things together. So in each modeling step, this function intervene, you can see, which is very short there, which accepts a step number, elapsed time, and state. We have an opportunity to modify the state before the next modeling step. So to do Brooks' law, we just need to do this. If the elapsed time is 110, let's add 5 people into the project, okay? So we've just said that on a day 110, we're going to put more people in and see what happens. Very, very simple. So here we go. We do that on day 110, add 5 new people, and we go from 286 days down to 283 days. 283 is less than 286. It is, isn't it? Yeah? It really is. Oh dear. Brooks' law turns out not to be a law at all. Actually, I think he just phrased it wrong, and I'll try to explain why. Let's play with the model a little bit more. Let's add some more people. So I added 5 people last time. Let's add 10 people now on the same day. Look how the time changes now. It shoots up to 307 days, right? This is nonlinear, highly nonlinear. Okay? So in this case, he was right. If we had enough people, Fred Brooks was right. Yeah, I'm going to skip this one. This is just showing the blue curve is the communication overhead function. They only did the experiment up to 30 people. I haven't been able to do the experiment for more people. So I just use a saturating function because you cannot spend more than all of your time talking. Right? It just allows us to play with the model without limits and see what happens. And of course, if we had 15 people, it begins to get very, very much later. Okay. But let's go back and take a different perspective on this. So we're talking about completion date, and that's what Fred Brooks was talking about. He said later, right? He's talking about completion date. It's more interesting to look at money. So I'm just counting money in terms of developer days, right? So if I add no people, it takes 288 days to completion, and it costs me 5,760 developer days, right? I can come in 1 day earlier by adding 5 people, but look at the cost, right? If Fred Brooks had couched his law in terms of cost rather than time, he would have been right. It would have been probably a law, right? But of course, as we get very much later by adding more and more people, look what happens to the cost. It just goes up to insane levels, okay? You can come in a lot later and spend twice as much money. It's great. Okay, I'm going to wrap up very quickly now. So that's the Brooks law model, or I think we need to call it something other than Brooks law until he's prepared to reformulate the language a little. What I've showed you comes from a field called software process dynamics, which is a very narrow, small field. I was attracted to it because I have a background working in industries where we make these kind of models for industrial processes. And so these kind of things are very common. The broader field of process dynamics is actually widely used for all kinds of things, like modeling the flows of patients into accident and emergency units, right? And then from the accident and emergency unit into the main hospital area if they are seriously ill, and then they stay in the hospital, and then they get discharged and go back into the community. So these kind of models are finding applications in all kinds of fields, not just flows of chemicals through processing plants. So I think it's interesting, just from a modeling point of view, just to remind ourselves that there are other ways of modeling the world rather than the very kind of discrete models that we deal with in domain-driven design, where everything is constructed from entities and aggregates, right? Sometimes we need to also model actual physical processes. So if nothing else, maybe you've learned a little bit today about different approaches to modeling. So this is a lot of fun. Is it useful? I'm very fortunate to be at this conference where the audience is both intelligent but notably very thoughtful. So I hope at the very least I've made you think about the way the world works and how our industry works, and some questions you might want to ask about it, and I encourage you to question some of the sacred cows that we have around, like Brooks' law. If you do, and I would encourage you not to take exact numbers from these kind of models. That is exactly the wrong thing to do. Do not use a model like this to tell somebody how long it's going to take to complete your project. That is a very silly thing to do, right? You should use models like this to simulate interventions you're thinking of making and then understand the quality of the outcome, right? So you can say things like, yes, this might make us earlier, or yes, it will definitely make us later, those kind of things. So use them to guide decision-making, and policies don't ever give people the actual numbers, right? That is going to lead to a lot of difficulty for everybody, including you. If you'd like to learn more about this, there are a couple of very expensive books on the topic. You should try to get them secondhand. One is called Software Project Dynamics, which I think you have to get secondhand because it's out of print. And there's a more recent book, which also includes a Brooks Law model called Software Process Dynamics. And this is essentially Raymond Madaki's PhD thesis converted into book form, and it is surprisingly readable. He has some very interesting software process dynamic models, which includes not just things like Brooks' law, but also the flow of defects and requirements through software development organizations. It's really fascinating. You can get my model implementation, which is a stunningly simple thing. It's very, very simple code on GitHub, and I am going to stop right there. Thank you very much.
You at 110 days, you add 5 developers or 10 developers. Why did you pick this?
Oh, why 110?
Yeah.
Right, it's just a number in the middle of between 0 and 230 or 240 or something. It was just in the middle. Of course, the question that needs to come after the question you just asked is, when should you add people, right?
Yeah.
Right? At the beginning or at the end. I don't have the slides to show it today. You need to download the model and play with it, but there are some very counterintuitive answers to that. Because if you add them right at the end, right, which is in the limit, if you add them at the very end, when you've already finished, it has no effect, of course, because you've already finished, right? So adding them very late in the project has no effect, right? Adding them very early in the project is great, right? So then the question is, what is the optimal time to add them? And there is an optimal point you can find, and you can use a simulator like this to find that, right? It's complicated, right? Even though it's a very simple model, it exhibits some quite interesting, complicated behaviors. So, and again, the point is about, I want to reiterate the point about using it to guide policy rather than give you specific numbers. It's like, oh, it's Wednesday, we need to add some people. It doesn't work like that.
Right now you looked at, you kept okay, so you're working as a project towards this amount of function points.
Yeah.
Or this amount of lines of code, always. Have you looked at models of how to predict how large a system needs to become until it's finished, or
I
is there
haven't
some
looked
convergence?
I haven't looked at that myself, and of course the model is naive because it assumes we know all the requirements at the beginning,
Yeah.
right? Which is never the case. So what you should really have with a model like this is a flow of requirements into the system as you go, as you discover stuff, and you also need a flow of another feedback loop from the developed code, because your developed code will be buggy, right? Mm-hmm. And you need to build that loop in as well, where you're spending some of your development effort on fixing stuff you've already built, right? So the model is undoubtedly, the model I've shown today is the simplest model which shows any interesting behavior, right? And of course you can, if you look in the books and the literature that goes along with this, there are some fantastically complicated models which try to incorporate all kinds of different interesting factors.